In this lesson, we will learn how to derive the short, long, and combined kinematics equations. And the first equation we will derive is the short kinematic equation. It relates velocity to time and begins with our definition of accelerations. A equals delta V over delta V, delta T. Acceleration is a change of velocity with respect to time. Let's expand this by replacing delta V with V final minus V initial. And now we have A equals V final minus V initials divided by delta T. Next, we will multiply both sides by delta T. This gives us A times delta T equals V final minus V initials. Isolating V final, we arrived at the final form of our short kinematic equations. V final equals V initial plus A delta T. Notice that the equation has the form y equals mx plus b, where V final is y, V initial is V final is y, V initial is b, and delta t is x, and a is the slope m. The second equation we'll derive is the long kinematic equation. It relates position to time. To derive this equation, recall that we define the average velocity as the displacement divided by the time interval. V equals delta x over delta t. For V equals delta x over delta t. For our derivation, we will need to define the average velocity in terms of initial and final velocity. Average velocity equals the final velocity plus the initial velocity divided by 2. The reason that we do this is because we need to use our short kinematics equation, and that does not include average velocity, only initial and final velocity. Now we can set these two equations equals, and we have delta x divided by delta t equals delta t equals V final plus V initial divided by 2. Now we will substitute in for V final, our short kinematic equation. This gives delta x divided by delta t equals V initial plus A delta t plus V initial divided by 2. Combining like terms, delta x divided by delta t equals 2V initial plus A delta t divided by 2. We can simplify to get delta x divided by delta t equals V initial plus 1 over 2 A delta t. Now we just multiply both sides by delta t to arrive at our long kinematic equations. Delta x equals V initial times delta t plus 1 over 2 A delta t squared. Sometimes it is written with the delta x expanded and solved for x final. Like x final is equal to x initial plus V initial delta t plus 1 over 2a delta t squared. So that means that position of an object at any given moment in time is equal to the initial position plus the initial velocity multiplied by the time interval plus 1/2 the acceleration multiplied by the time interval squared. Notice that the equation has the form of a quadratic. For example, y equals ax squared plus bx plus c, where x final is y, A is A is A, and T is X. V initial is B, and X initial is C. Our third kinematic equation relates velocity to position, and it is called the combined kinematic equations. We have not yet defined such a characteristics of motion up to this point. Our motion has been related to time. To derive this equation, we must eliminate time. We can do this by substitution. We will combine our short and long kinematic equations by solving the short equation for time and substituting it into the long equation. So V final equals V initial plus a delta t becomes delta t equals V final minus V initial over A. Then we replace all of the delta t's in the long equation with these equations. So delta x equals V initial delta t plus 1 over 2a delta t squared becomes delta x equals V initial times V final minus V initial over a plus 1 over 2a times V final minus V initial over squared. This distributing terms we get delta x equals V initial times V final divided by the minus V initial squared divided by a plus divided by a plus 1 over 2 a times V final squared minus 2V initial V final plus V initial squared divided by the squared. Simplifying, we have delta x equals V initial times V final divided by a minus V initial squared divided by a plus V final squared divided by a 2a minus V initial V final divided by a plus V initial squared divided by 2a. Combining like terms, we get delta x equals V final squared divided by a 2a minus V initial squared divided by 2a. Solving for V final squared, we arrived at our combined kinematic equations. V final squared equals V initial squared plus 2a delta x. Now, we have an equation that can be used to define the motion of an object in cases where we do not know the time interval. The equation covered in this lesson are the foundation to our study of physics. We will use these a lot in this course. Here they are together. We saw the short kinematic equation. V final equals V initial plus a delta t, the long kinematic equation, and a new average velocity equation. Delta x equals V initial delta t plus 1 over 2 a delta t squared, and V average equals V final plus V initial divided by 2. And the combined kinematic equation, V final squared equals V initial squared plus 2a delta t plus delta x, 2a delta x. And the combined kinematic equations, V final squared equals V initial squared plus 2a delta x. Thank you for watching.